morning, the organizers. Sorry, people who are online. Don't hesitate to interrupt me. The same for people in the room. And also thank you, Eva. You do the job for my talk. Most of the model is very similar. Yes, and it's a collaboration with Quentin Cormier and Romain Vels. Okay. What is our goal? Our goal was to study mathematically a model of network which has the following properties. We consider only excitatory interaction, and we want to prove that with such a network, it's possible to observe oscillations. Okay, I'm not a biologist, but it's clear, I understand that it's clear that we always observe oscillation when we measure the membrane potential in vivo, and a mathematical model without oscillation has to be rejected. I don't thank you, Olivier, for your comment today morning about the integrate and fire models. Here, we'll prove that an integrate, a generalized integrate and fire model can have permanent oscillation even if we only consider excitatory interaction. Okay, you know, it's very clear that if you have inhibitory neurons and excitatory neurons, it's very easy to understand that first the excitatory neuron spikes, then the inhibitory one, and you see that the activity of the network has oscillation. Okay, we are mathematicians when a problem is too difficult to solve, and it's the case of the finite system of neurons. We try to solve the problem with a less complex model, and here I don't know if it's less complex, but it's easier to simulate. So we consider the limit system when the number of neurons goes to infinity. It's the mean field model. And the question is, what is the behavior of this kind of mean field model? So first question, what is the long-time behavior? The question of the long-time behavior is maybe not the most important one, but it's a way to touch the stable state. Okay, so the next question are, are we able to give a precise description of the invariant measures? Second, these invariant measures, are they stable? And if they are not, what can we observe? And the conclusion, I give you the conclusion in the introduction, we observe oscillation for some very particular values of the interactions. Okay, here is the outline of the talks. First, I will describe the particle system, and it's a repetition of the model presented by Eva, more or less a little simpler. And then I give precise result about the convergence of the solution to this equation when time goes to infinity for small interaction. And we'll discuss the stability for any interaction and illustrate the fact that we can observe oscillations, that is periodic solution. Okay, the model is here. So we have capital N neurons, and we only consider it's okay. I'm sorry, it's impossible to speak. You can go far if you want. We have capital N neurons, and we only consider their membrane potential. So we assume that the neuron is a point. Okay, it's not a very good model for an individual neuron. Our goal is to understand the global behavior. So we can simplify, and we will simplify a lot, the behavior for each individual neuron in order to understand the global activity. So between the spike, it's nothing else, a simple dynamical system. So dVt over dt equal b of vt for any neuron with the same function b. Okay, and in practice, for numerical example, you can take B constant or B linear, but for an EB it works, and we have exact expression for an EB. Each neuron I spikes randomly at rate. I need to repeat because we changed notation. So the spiking rate here is f of v. It means that the probability to spike during a small time interval of length dt, this probability divided by dt converges to a quantity, the spiking rate. And here, I don't know if Antonio will give a comment. We reset the modern potential when the neuron spikes. Okay, so we are mathematicians. We normalize this quantity.
Antonio is very happy. Antonio is very happy.
Thank you. The test. Yes, there is that. It's the VF in Alejandro talk today morning. Is 0. And in fact, 0 was equal to 1 today, at the end of the talk. And, sorry. When one neuron spikes, it has an effect on the postsynaptic neurons. And to simplify, here the synaptic weights are J. Sometimes it's W. We prefer JW for the Brownian motion, usually. Okay, so here is the setting. A wonderful illustration. I have to thank Quentin for this picture. So you have a typical trajectory of a big network with two neurons, the red one, the blue one. As you can see, when the blue one spikes at this time, the red one has a small jump of size J1, 2. And next, it's the red one who has a spike, so you can observe a jump here, and so on. Okay. So the model is fully described with a very few quantities, very few, yes, parameters. First, the drift. And we only assume that B of 0 is positive, such that you don't stay at 0. In the previous talk, it was Eva has assumed what she needs in order to have 0 as an invariant measure. We refuse to have an invariant measure at 0. So we assume that B of 0 is positive. Second, we need to find the rate function. So a link with the talk given by Alejandro today morning. For this setting, it's f equal to plus infinity for v larger than vf. I think vf was equal to 2 today morning. And is equal to 0 for v smaller than vf. So here we have a generalization. I don't know if it's a generalization, but we know that the statistics statistician and measurement refuse the yes, it's time. The integrate and fire model with a fixed threshold. So it's a way to observe a spiking network with without this fixed threshold. Okay, the connectivity matrix and the law of initial condition. Oops. Okay, I don't know if I'm able to say it, but we simplify the network we consider that the Holtz interaction are equal to their mean value. Okay, so we are exactly in the same setting. And first, the first question is, what is a good scale for this mean value of the synaptic weights, such that at the limit, you have non-trivial interaction. Non-trivial means they are not equal to 0, nor equal to plus infinity. And we know, it's very well known that the scale is a constant over n. So as n goes to infinity, as usual, the sum of the stochastic integral with respect to Poisson measure converges to the expected value of the same quantity. So you recognize here E of f of vt. And we keep the jump to the limit model. That is, our typical neuron spikes at rate f of v. Okay, and the question now is, what is the long-time behavior of this Makin-Vlasov process? They are maybe not in the room, but our colleagues studies usually exactly the same question from a deterministic point of view. How does it work? We denote the law of our moment potential, okay, denote it by nu, and we are able to write the evolution of the measure nu as time evolves, and it's written here. So it's a nonlinear Fokker-Planck equation. Why is it nonlinear? It's nonlinear because here in the drift part, you have a quantity which depends on the law of nu. It does not only depend on the value of nu at position x, but it depends in a macroscopic quantity, here E of f of xt, I'm probabilist, in the drift term. Okay, and second is this. It's the strong form, so if the initial condition has a density, we can prove that this property is kept in time, and we write the PDE satisfied by nu here, again, the Fokker-Planck, the nonlinear Fokker-Planck equation, and we have a boundary condition which gives a link between the value for any time t at reset potential, V of t and 0, as a function of this global quantity, the spiking rate, R tilde nu of t. Okay, a few words on the previous work on this topic. So first, I think the first mathematical study of this model was by Demasi, Galvez, Locherbar, and Presutti. Then Fournier and Locherbar studied an extension of this model for more general initial condition. And then the third work is by Audric Drogoul and Romain Velt. It was more or less a numerical study of the model in Fournier and Locherbar paper, and they proved this kind of oscillation numerically. And last reference is an example of Makin-Vlasov of nonlinear diffusion where we can observe this oscillation phenomenon. Okay, what are the invariant measures of our stochastic process, nonlinear stochastic process? So I write again the equation for the membrane potential, and the first remark is that if the initial condition is invariant, E of f of vu does not depend on u, so I replace it by alpha over j, so that I replace j times E of f of vu by alpha here. And as okay, the problem is solved. We have a linear equation, and it's easy to study. It's more easy to study a linear equation, and the exact solution for, the exact invariant measure for any function f and b with very few assumptions on this function is given by this expression. And the support of this measure is up to the first time at which alpha plus b is equal to 0. You see here you have this 1 over b of y plus alpha. You can imagine that there is a critical point where b plus alpha is equal to 0. Okay, gamma is a normalization such that you have a probability distribution, and we can prove that gamma of alpha, it's very easy to prove, more or less nothing to do, to prove that this normalization is equal to E of f of y under the stationary distribution. So we solve this linear equation, but is it a solution to the nonlinear equation? And it's very clear that if j times gamma of alpha is equal to alpha, you can here replace alpha by j gamma of alpha, that is j times e of f of y alpha. And it means that if this equation is satisfied, y is also a solution to the nonlinear equation. Okay, first result. J'ai une demi-heure. First result. There exists a unique solution to the nonlinear equation. Second, for small interactions, that is for small parameter j, whatever the initial condition is, the law of the solution converges to these unique invariant measure, that is the new infinite alpha given there, where alpha satisfies this equation. Okay. So the question now is, if you have a j, are there a solution of this equation alpha equal to j times gamma of alpha? So here is a simple illustration for a toy example. So B is linear, F is a quadratic function, the rate function is quadratic. And we see that for small j, less than this value, we have only one alpha such that j of alpha equal to alpha over gamma of alpha. If you are larger than this line, it's the same. And between, you have exactly 3 solutions to the equation alpha equal to j times gamma of alpha. In the first case, we have one unique invariant measure. For the intermediate case, we have 3 invariant measures. This one and this one are stable, and the intermediate one is unstable. Okay. The second example, okay, the drift is still linear, but F is less Lipschitz continuous than before. We take x to the 10. It means we refuse f equal to infinity with this R threshold, but we want to force to spike when the value of the moment potential is larger than 1. We can prove that for any j, there is exactly one invariant measure, but we observe numerically that for j in this interval, our simulation shows spontaneous oscillations. And these oscillations are robust. Okay, so here is an illustration. So we simulate the interacting particle system with 10,000 neurons. Sorry, Christophe. And here is a raster plot for the 500 first neurons in the system. And what you can see is that the activity does not seem to be constant in time. In fact, here is the spiking rate, the empirical spiking rate, and you observe this oscillation. Okay, the initial condition is particular. So after a short time, say after 5 seconds, I don't know what seconds means here. After time t equal to 5, you can observe robust oscillation, and these oscillations never disappear. So a few, I need to introduce what we mean by the distribution converges to the stationary distribution, and the definition is written here. So we assume that the current, J times the rate, is the external current, not external, internal in the neuron, external for the viewpoint of one individual neuron. So if the current converges to the stationary current, alpha, at an exponential rate, we say that okay, again, if for a distribution in a neighborhood of the stationary distribution, we can prove that the current converges exponentially fast to the constant stationary current, we say that the environment is locally exponentially stable. And Quentin proved in a paper that the quantity you have to consider is equal to, so I wrote both expressions, the first one with the function, the second one with the stochastic process. If you differentiate with respect to the initial condition, the spiking rate at time t for the linear process with a constant current equal to alpha, and you integrate the initial condition with respect to the stationary distribution, you consider the Laplace transform of the previous quantity, and you solve the equation j theta hat of z equal to 1 if all the solutions of this equation have a real part which are negative, then the stationary distribution is exponentially stable. Okay, some idea of the proof. First, we consider a generalization of the linear equation where you allow to have a constant current which depends on time. So we replace this j times e of f of yt by a quantity which is assumed to be known, a of t, and we study this equation with the spiking rate given by this r a nu. And the first property...
Etienne, I'm sorry, we can't see the slide. We see the entire room, but not the slide. Something is wrong with the transmission.
Thank you.
Well, perfect.
It's okay now? Okay. So very fast. We can prove very easily that the spiking rate solves the Volterra equation. It's very easy to understand. We just consider U as the last spike of a typical neuron. And okay, the first term is the probability to spike if you have never spiked between 0 and t. And this integral is the integral of the spiking rate where U is the last time your neuron spikes. And again, if this equality is satisfied, you have a solution to the nonlinear equation. And when you want to conclude if there are stability or not, you start close to the stationary distribution, and you evaluate if the spiking rate of if the evolution of your process stays close to the initial one. Ah, la, 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 la. So the idea is to prove that, okay, you can first make computation. It's what Quentin did in the first paper. Then he understood better the behavior of this equation. And in fact, the two quantities, the theta introduced on the previous slide, is the Lyon's derivative of E of f of yt when you change a little bit the initial distribution. Well, it's differentiation with respect to the initial condition. The same for the rate for the nonlinear process. And he proves that you also have a Volterra equation between these two quantities. It's written here in the resolvent form. And when you compute the Laplace transform, you see that omega hat is equal to j theta hat over 1 minus j theta hat. Okay, it's not a proof, but you can understand, thanks to this proof with and, that the zero of 1 minus j theta hat has a role in the evolution of this. Okay, two very fast remarks. The first is the condition to be able to decide if the stationary distribution is stable or not. We only need to study the linear equation starting from a deterministic point with a constant current. So it's more simple context. And second, okay, as usual, you have a theorem. If some condition is satisfied, then you have sometimes what is after if is empty. So here we can prove that if in particular case where f plus b prime is non-negative, the criterion is satisfied. And so the stationary distribution is locally stable. Okay, here is a picture with a zero of j theta minus 1, theta hat minus 1. And you see that the real parts are negative. Oh, wonderful movie. You see the evolution of the distribution of the membrane potential as time evolves, and after a short time, nothing happens, and you are very close to the stationary distribution. Okay, it was for j equal to 0,71. We change a little bit j. Ah non, c'est entre les deux. Okay, here, sorry, the previous one was for this value of j. Then it's for this one, and you see that the two roots of this equation have real part equal to 0. And for these values, okay, I don't have time, so I will stop the movie. But if you wait a long time, it always has the same behavior with this kind of oscillation. Okay. Mais combien de temps, Olivier? 2 minutes? À peine? Je dois avoir fini. Okay, so here is the bifurcation diagram. You see here there are two values, and our choice of J in this area, you can observe that the current oscillates between these two red curves. Okay, we have a precise mathematical result, which is written there. So you consider value alpha 0 such that you have a solution to your equation. And if there is a zero of this equation with real part equal to 0, it's written here, such that you cross the line when you change a little bit the value of z, then we can prove that, so here is the theorem, we can prove that for v equal to 0, you have this stationary distribution, but if you change a little bit the value of v, you can construct a set of distribution nu v, which depends on t, which are 2p periodic. So it's the oscillation you observe on the movie. The period depends on the value of the parameter. And okay, the value of the current also depends on it. So we construct in a neighborhood of this special point solution which oscillates periodically. Okay, so it's given here. So I repeat almost the same. And this alpha v is the mean value of the current over a one period. the end, I thank you. And here are the references. So the first concerns the study for small value of the interaction. The third one, the oscillation of the system close to this value alpha 0. And the second, the last one, the work of Quentin, in which he proved precisely that the criterion is a good criterion when you want to study the behavior in a neighborhood of stationary distribution. I thank you, and I'm sorry for the delay.
Thank you for this nice talk. Questions from the audience? Yes, Vera?
So I have two questions. So the first is, in the end, you show you have these periodic solutions. Do you converge to them? I mean, are they globally attracting locally? Or, I mean, do you...
Yes, no. No. Yeah. What is your question? Do we prove that?
Yes. Did you?
If you start, no, we prove that this, I mean, this set of distribution is a periodic stationary solution. We did not study if you start in the neighborhood of one of these distributions, you stay.
Because there you have a continuum actually of periodic solutions, no?
Yes. Okay, there is uniqueness. Okay, so it's maybe... we need to go back to the initial equation. Okay, so this one. Here, when we say we obtain new solution, we change a little bit the value of J. Okay? So, but in practice, usually you fix J and you study the system. So if J is chosen in a neighborhood of J of alpha 0, then you observe oscillation. But okay, I didn't answer your question if we are able to prove that it converges. I can only say that numerically, we cannot... Okay, we always observe these oscillations. You had a second question?
Yeah, I had the second one. I mean, this nice criterion of Quentin of periodic solutions or not. So you say the new interpretation is you take the mean spiking rate, as I mean, in the stationary regime, you derive with respect to the measure.
Exactly. It's exactly the same criterion, but he is now able to explain why, I mean, to explain to my grandmother, I mean, without precise computation, just to differentiate with respect to the initial condition, what is the quantity, what is the value of this.
Okay.
And in fact, it proves in a diffusion setting, but it's the same idea.
More questions from the audience? Patricia.
Thank you, Etienne. I have a naive question, and maybe you answered at the end, but it was too quick for me. The period of your periodic solution, does it depend only on J, or does it depend also on F?
No, F and B are fixed.
No, but I mean, if for instance, I'm dreaming of having several different rhythms in your in the brain, say, could I just play with J and somehow have different connectivity and then get different frequency with the same F?
Yes, with the same F and B, if you change a little bit J, the value of the period is not the same.
Okay, and then it's, well, is it still bounded, or can we really
Yes,
like
yes.
travel around several order of magnitude by just playing with J?
I don't know. I'm sure that everything is bounded here. But you see here the value of the current.
Okay.
It does not give you the period. But,
Okay.
okay.
Thank you.
I have a very naive question. In your theorem, you exhibit a V0, and can you quantify it? Or
No. It's a theoretical result when you have a function with a non-zero derivative somewhere. We apply the implicit function theorem to prove that we can inverse some function. So we have no. I mean, if you want, I can spend some time in order to study the value of V0, but here there exists a V0 such that I mean, in a neighborhood of alpha 0,
okay.
I have this behavior. But
Oh, there's a question on the internet. Go ahead. Go ahead.
I can read. It's a question by Zelan Zhu. It says, thanks for the wonderful talk. For the specific examples you have shown, is there a way to prove the existence of the sites numerically? In other words, is there a way to
okay. No. But we put an example in the paper published in EJP, for which we are able to make completely the computation, and we prove that we are able to find the zero of this Laplace transform of the derivative of the. So we have one example for which we are able to prove that the condition is fulfilled. But it's really a toy example. So I didn't want to show you. Okay, okay. The talk is not very close to the behavior of neurons, but our example is less close.
Well, thank you, Etienne. There are no more questions. Let's thank the speakers of the half session.